Okay, um, we're going to start off. I think that this lesson is pretty doable, pretty easy to consume. Okay, the essential understanding here is that you can use the ratios of the lengths of a side to um, compare the perimeters and areas of similar figures. And here's the idea, and we'll put it into practice in a second. Okay. Um, if the scale factor of two similar figures is a to b, where a is the measure of a side length of the first one, and b is the measure of the corresponding side length of the second one, then their perimeters will also have that exact same ratio. Okay, perimeters are in one dimension, so you get each of those values to the first power, or what they are. Okay, their areas though, areas is in two dimensions, the units are squared, and so the similarity ratio is also squared. So you get, if you had a similarity of, like, if one side, let's do a triangle, okay? This should make sense to you, okay? If we have a side length of 3 and a side length of 4, we've got an initial side length ratio of 3 to 4. Now, let's say it was an equilateral triangle, so this was 3, this was 3, this was 4, this was 4. Then what happens when you do the perimeters? Sorry, we can do better. Okay. Then the perimeter of the first one is 9. The perimeter of the second one is 12. And that simplifies down to 3 over 4. That's just what the ratio of a single side was. Okay. Now, how about the area? Excuse me. Well, without worrying about what the uh, area is by calculation, like I don't want to have to go through the work of using trigonometry to do the calculations, but watch what happens here. You essentially take the ratio of a side length, or the ratio of the perimeters, which is 3 to 4, and you square it. You can either say like times, squared would be like times 3 over 4, right? And what you get is 3 squared over 4 squared, or in this case, 9 over 16. So their areas will have a ratio of whatever the side length ratio is, a over b squared, a squared over b squared. That's the gist of it, okay? And even though we're going to be applying that all day long, the concept is real basic and real fundamental, and I think that you'll do well with it. So let's apply it. Let's see where we go with this. Okay, let's apply this. So finding the ratio in similar figures. These are similar, and the scale factor is the side length of 6 over the side length of 9, which simplifies to 2/3. So they have a scale factor of 2 to 3. Okay, what is the ratio, smaller to larger, 2 to 3, of the perimeters? Well, remember, perimeter is just the same scale factor because it's in one dimension, so we raise each one of those to the first power. 2 to the first power is 2, 3 to the first power is 3. You don't really need to raise it to the power. I'm just showing you what you do, like how you think of it in terms of the same rule that you apply for eventually areas. So the ratio of the perimeters is the same as the ratio of a corresponding side, 2 to 3. What is the ratio, smaller to larger, of the areas? You square the top and square the bottom, so the ratio of their areas will be 4 to 9. Super straightforward. Okay, here's your got it problem. Two similar polygons have a corresponding side ratio of 5 to 7. And now watch what they're saying. Make note, they're saying larger to smaller. Okay, what is the ratio of their perimeters? Larger to smaller. And what is the ratio of their areas? Larger to smaller. Pause the video now and unpause it when you have your answer. Okay, so if they're saying larger to smaller, the perimeter, remember the perimeter is the same as what the side ratio is. So since they want it larger to smaller, instead of writing 5 to 7, we're going to say 7 to 5, or you could write 7 to 5, or 7 to 5, either one of those, okay? And what is the ratio larger to smaller of their areas? Since we're squaring them, I'm going to write it like this. And remember, we square it, each one of them, and we get 49 over 25. If you're wondering, can I simplify that? Well, if you could, there must have been a common factor that was existing here already. Can you simplify 7 over 5? No, you can't. So you're not going to be able to simplify 49 over 25 either. Okay, so this becomes the answer for A, and this becomes the answer for B. There you go. Let's keep going. Okay, so here, problem 2, they're saying that we're going to find the area of these similar figures. The area of the smaller regular pentagon right here is about 27.5 square centimeters. What's the best approximation for the area of the larger regular pentagon? Okay, and we know what their side length ratio is. So they give us all these options. Okay, and just looking at those options, can we eliminate any of the answer choices immediately? Yeah, we're already given the smaller pentagon's area as 27.5. Okay, so a larger pentagon is going to have to be have a larger area, so we can immediately eliminate choice A. Yeah, you should be able to make sense of that idea that it can't be smaller if the thing is larger. Now, how do we do this? Well, notice this. We know what the side length ratio is, right? If it's a 4 to 10, or we can simplify that to 2 to 5, then they have a ratio of 2 to 5. How do we know that the polygons are similar? Well, they're regular pentagons, right? And regular pentagons are similar because all of the angles measure 108, right? They have a total of 540 degrees divided to the 5 angles equally. And all sides in each pentagon are congruent. We know that because it says it's a regular pentagon. Okay, so we have their ratio of corresponding side lengths of 4 to 10, 4 to 10, right? And therefore, if we simplify that to 2 to 5 and we square it to find out what the area is, we get 2 squared, or 4, over 5 squared, or 25. So we know that they have an area ratio of 4 to 25. So we can say, okay, we can come up with a similar ratio by saying 4 over 25 equals the 27.5 area corresponds with the small one. Since the small one area is on top, 4 to 25, we put that on top. Okay, 27.5. And on the bottom we say they're using A for area. What's the area of the larger one? Okay, well, if we cross multiply, we get 4 times A, or 4A, equals 25 times 27.5, 687.5. They call that the cross products property. Dividing both sides by 4, we find that it has an area of approximately 171.875, and if we round it to the nearest unit, the area of the larger pentagon is about 172 centimeters square. You see that here for answer C. So let's mark it. That's the right answer. Okay, and again, what we did there is we said if they have a side length ratio of 4 to 10, or 2 to 5, to find out the ratio of their areas, we square that, 4 over 25, and we set that equal to some ratio of their areas where the 27.5 corresponds with the top, because the top is where we have the smaller pentagon's area. Okay, and then do the algebra to solve it and find your answer. Okay, here's your got it problem. You're going to pause your video and you're going to solve this, and then when you have your answer, and of course there's no multiple choice, so you got to come up with the answer on your own doing the same process, you are going to unpause it and check your answer against mine. So pause the video now. Okay, so we've got a scale factor of 2 similar parallelograms. The scale factor is 3/4. The area of the larger parallelogram is 96. What's the area of the smaller? So if we want to know what the ratio of their areas is, we need to square it. So if you square 3/4, or 3 squared over 4 squared, you get 9 over 16 is the ratio. Okay, so we can say, okay, then 9 over 16 is equal to, which one do we put on top and which one do we put on the bottom? Well, obviously the larger one's on the bottom, it's the larger number. So if they say the area of the larger parallelogram is 96, that's going to go on the bottom. And we're going to put x here. Okay, so then we have, if we do the cross products property, we have 16x equals 9 times 96. Let's see, 9 times 9 is 81, so 810. And 9 times 6 is 54, so 810 plus 54 is 864. And of course, if we divide both sides by the coefficient of the variable, 864 divided by 16 gives us an x equals, gosh, let's see, 54. Yeah? X equals 54. So we have as the area of the smaller parallelogram is, if we were to write it using the units, we would say it would be 54 inches squared. Okay. Yep, that's how you do it. Let's keep on moving and see what else they got for us. Okay, so now we're going to apply this to a real life problem. And here it says, during the summer, a group of high school students cultivated a plot of city land and harvested 13 bushels of vegetables that they donated to a food pantry. Next summer, the city's going to let them use a larger, similar plot of land. In the new plot, each dimension is 2.5 times the corresponding dimension in the original plot. So the scale factor is 1 to 2.5. How many bushels can the students expect to harvest this year? Well, first things first, we don't know the shape of the plot. So is that going to be a problem? Because we've been using geometric shapes. So do we need to know the shapes of the two plots? Nope. As long as the plots are similar, we can compare their areas using their scale factor. So that's great news. We don't need to know that they are shaped any particular way as long as we know that they're similar. Okay? So how do we do this? Well, the ratio is, if we're doing the larger to smaller, is 2.5 units for every 1 unit on the original smaller plot of land. So their area is going to be 2.5 squared to 1 squared, or 6.25 to 1. Okay? So with 6.25 times as much land as next year, the students can expect to harvest 6.25 times the amount of bushels, or about 81 bushels. Okay, got it? So here's your got it problem. Scale factor of the dimensions of two similar pieces of window glass is 3 to 5. The scale factor is 3 to 5. The length of one side to the length of the other side is 3 to 5. Okay, we're now talking about areas because window glass is a two-dimensional flat surface. Okay, so if that is their scale factor, we're going to need to come up with the area ratio, because the similar piece costs, the smaller piece costs 250. How much did the larger piece cost? That's the first one. Now, in problem 3, why is it important that each dimension is 2.5 times the corresponding dimension of the original plot? Explain. Okay, so work on this first. See if you can understand this question. So pause it, be looking at the question. Okay, in this problem, why do we need to know that each dimension is 2.5 times? Okay, and we'll explain that. But pause the video, try and calculate this one out first, and unpause it when you have an answer, and we'll go over it. Okay, so if we have a scale factor of 3 to 5, then we need to do 3 squared over 5 squared to find out what the area ratio is, and we have it as a 9 to 25 ratio, right? So if we say, okay, 9 to 25 scale factor equals a cost for that area of 250, what will be the cost of the larger area, right? And we get 9x equals, let me see if I can do this in my head, 25 times 250 is 6250. Sorry, 6250 with a decimal there. And that was the cross product property, multiplying that times that equals that times that. I happen to know that 25 times 25 is 625. So 25 times 2 is 50. It's going to be a little larger than that. Same numbers, same digits, just with the decimal in the right place, so it's got to go there. Okay? Now, if we divide both sides by 9, we get 9x divided by 9 equals 6250 divided by 9. And therefore, x will equal, and I'm going to do the math over here on the side, and then I'll erase it. 6250 divided by 9. Let's see, 63, it's close to 63, but it doesn't go in 63 times, so I'm going to say 9 times 7 was 63, so 6, right? That's 54. We get an 8. If I'm doing it right, we should always get a number here that's smaller than what I'm dividing by, otherwise I could have gone a higher number. Decimal comes straight up, bring the 5 down, 9 goes into 85 9 times, that's 81. 4 left over, bring down that 0. 4 goes into, I'm sorry, 9 goes into 40. Let's see, 36 would be 4 times, right? And that would be a remainder of 4, so we'd get a 0.444 going on repeating. So roughly the larger piece should cost $6.94 when rounded to the nearest cent. Okay? And the last question here, why is it important that both dimensions are 2.5 times larger? Because really what we need to do is we need to say, okay, if you have this size, and we're going to this size, then every little one chunk has to be 2.5 times bigger in each direction in order for us to be able to square the ratio, right? If we had 3 to 5 and we only did it in one direction, we would say, okay, well, that's like saying this is the original area, right? And if we only make it go from 3 to 5 in the larger direction, then and the width stays the same, then we now, that side that was 3 is now 5, and we're now just going to get an area ratio of 3 to 5, okay? But if you said, oh, we're going to do it in both directions, going from 3 units to 5 units, I'm running out of space here, so I'll do it there, then that's when you truly get 9 units here equaling 25 units here. So only going in one of the two directions by 2.5 would really only get it 2.5 times bigger. I use 3 to 5 for simplicity's sake, but so in order for you to square the scale factor, you need to be making both dimensions that much bigger by that scale factor. Okay, cool. Let's keep going. Okay, so let's find the perimeter ratio if we know the area ratio. The triangles to the right are similar. What is the scale factor? What is the ratio of the perimeters? Well, if the area is 50 over 98, we know that. We need to know the scale factor. We're going to write it as proportions. Okay, we know that a squared is 50 and b squared is 98. Now, these aren't nice, neat square numbers, but check it out. This is a fraction that can be simplified, right? These are both multiples of 2. So if you divide top and bottom by 2, you simplify it down to this, and now, aha, it reveals itself to be two numbers that are perfect square numbers. Okay, and 25 is a perfect square of 5, 49 is a perfect square of 7. Okay, we have to square root them, and it's always the positive square root. Remember, it's true that the square root of 16 could be either positive 4 or negative 4, because negative 4 times negative 4 is also 16. But we're going to disregard that idea for having both answers because we're talking about length, and length is always positive. Okay? So we're going to take the positive square root of each side, and we get a scale factor of 5 to 7. So if that's true, then the ratio of their perimeters is just equal to the scale factor. If the scale factor of a side length is 5 to 7, then the perimeters have a scale factor of 5 to 7 as well. Okay, so you may need to simplify the area ratio first in order to get it down to numbers that you can then square root. Keep that in mind when you do this got it problem. Right now, you're going to do this got it problem and pause it and come back when you have your answer. The areas of two similar rectangles are 1,875 and 135. Okay, what is the ratio of their perimeters? So, pause the video, set it up, simplify it, square root it, and get your answer for the ratio of the perimeters, and unpause your video when you do so. So pause it now. Okay, so I'm going to write the original ratio, 1875 over 135. I have a calculator here. I'm going to divide them top and bottom by 5. And when I do that, I have a calculator, let's see, 1875 divided by 5, because I can see they're both multiples of 5, I get 375. And 135 divided by 5, I get 27. Okay, 27 is just 3 times 3 times 3, so if I can't divide the top by 3, then I'm done. But actually I can. When I look at this, I know that if I add up all the digits and it adds up to a multiple of 3, the whole thing can be divided by 3. So 3 plus 7 is 10, 10 plus 5 is 15, and 15 does divide evenly by 3, so I can divide them both by 3. So I'm going to write divided by 3 over 3, which is the fancy form of 1, and 375 divided by 3 equals 125 over 27 divided by 3 is 9. Okay, so I know that this 9 is just 3 times 3. Okay, and I know that this is just 5 times 5 times 5. So there's no way, there's no common factor that I can divide them any further. Okay, so since this is the simplified area ratio, I need to square root top and bottom to get the ratio of the perimeter. So I say square root of 125 over the square root of 9, and fun fact, that's the same as 5 times 5 times 5. Gosh, sorry, I can do better. Over the square root of 3 times 3. Well, if I see something in there twice, I can bring it out once, right? So I say, I can see that 3 in there twice, so I can bring it out once as a 3, and there's nothing left over. This 5, I see it in there twice, so I can bring it out once, but there's still a 5 in there. And that then, it seems weird, but that is our ratio of our perimeters, is 5 root 5 units for every 3 units on the smaller. It seems bizarre, but again, you need to do what you know you're allowed to do here, which is first simplify the area ratio to get it down as simplified as it can be. And then you got to square root each number. And this square rooted is this square rooted is this. That becomes your answer. Okay? So that's how you do it. Don't be afraid of this kind of stuff. This is higher level math, just involves this stuff. And what does this mean actually? Well, this is a perfect way of writing a number that's not nice and neat. If you did the square root of 5, the square root of 5 is roughly 2.236. Okay, so when you multiply that times 5, that's, oops, I'm going to just change the setting on my calculator for a second. Okay. That is 2.236 times 5, 11.18 roughly. Okay, but not exactly. This is the only way to write it exactly. Yep, So don't be afraid of these radicals. You're going to come up with them a lot in the higher level math. But that's how you do this math. Good luck. Let me know if you have any questions.